Thank you all for coming today to our third Luminary series at the 2013 NSS Convention. My name is Gary Schindel. I'm the Administrative Vice President with the NSS. I'm glad to see a great crowd today. I would ask you all, we do have a couple of housekeeping issues. One is please be aware that we're filming this, and so be aware of that if you need to get up or leave or whatever. The camera is there. If any of y'all are in the witness protection program, don't walk in front of the camera. Then the other thing is if you all would check your cell phones, and if you all would put them on vibrate or turn them off, we'd much appreciate that. So thank you all for coming, and I'd like to introduce Dave Hughes. Thank you.
Good afternoon, ladies and gentlemen. Our speaker today is Dr. Rane Curl. Way back in the summer of 1952, the future Dr. Curl found himself as an MIT graduate student working at a DuPont facility outside of Charleston, West Virginia. But unlike any of the other engineering graduate students I've ever met, the future Dr. Curl apparently had some residual bandwidth on his hands because he actually had time for a real girlfriend. As luck would have it, the girlfriend's brother was none other than the legendary West Virginia caver, John Bud Rutherford. And before long, Rane, Bud, and Bud's good buddy Bob Handley were caving together in West Virginia. Shortly after receiving his degree, Rane moved to the West Coast to work for Shell Development Company. And while there, along with the likes of Bill Halliday, Howard Shugart, and George Moore, founded the San Francisco Bay chapter of the NSS. Rane has always had an interest in international travel, and at one point actually embarked on a 12,000-kilometer motorcycle tour of both Eastern and Western Europe. And some of the skills that he accrued during that trip no doubt helped him be the chairman of the 1981 International Congress. Domestically, Rane has made many contributions to the NSS. One is that he is the co-author of the original NSS Conservation Policy. He also edited the first 4 issues of American Caving Accident. Because Rane is in fact an engineer rather than a pure scientist per se, he has a very interesting perspective on some cave science issues. And as a result has done research and published on things such as the statistical distribution of certain cave entrance metrics, the calcite aragonite problem, the relationship between scallop size and water flow velocity, and speleothem aging and dating. As an administrator, Rane has served us as the NSS president. At the time that Rane took over the reins, the NSS administrative functions were scattered in boxes throughout the country in members' attics, basements, spare bedrooms, and so forth. As this became increasingly unworkable, Rane is the man who actually shepherded the transition from such a diffuse administrative structure to putting those things actually in a single real building, in a real office, with a charming address of Cave Avenue. So thank you for that, Rane. Rane is an exceptional engineering educator, a very enthusiastic adventurer and traveler, and a long-time contributor and administrator to the NSS. Please join me in welcoming 2013 NSS Luminary, Dr. Rane L. Curl.
I gave a lot of thought to being a luminary and what I should discuss and show and so forth. And really these are autobiographical presentations. And so I thought back that I joined the NSS in 1952, and therefore it's been 61 years that I have been in the NSS. And a program of this length takes about 61 slides to present. And therefore I had to choose 1 slide per year. Now, I admit I failed in doing that. I am going to have more than 1 slide for some years, but this also means that there are large omissions. And in fact, the biggest omission is the very beginning of my starting to cave. I didn't take any photographs at all when I was in West Virginia at the time, and not until I got back to Massachusetts did I actually begin doing some photography. But then there are big gaps following that, as you'll see in the presentation. So without any further ado, as they say, I'd like to set up the slides and begin the presentation. As I said, I don't have slides from the beginning of my career in caves, so I really have to start after I got back to Massachusetts. And we will move now to my career in New England and beginning of caving. And I was very fortunate, and I have been very fortunate throughout my career in cave exploration and speleology, to meet up with a lot of people who are luminaries in their own right. They could be mentors, I might say. Down here is Tom Barr, and he took us and took me to one of my first caves in New England. This is Indian Oven Cave in New York. And so I had joined up at that point with the Boston Grotto, and we had to develop some techniques for cave exploration. And there is how you did it in 1953 or so on 5/8 Manila. That's a 65-foot shaft drop into Benson's Cave. And then we had to find out ways to get out again. I can't see the button, I'm sorry.
Right here.
Okay. And so we had to invent some technology for doing that. The description of the Prusik knot had not yet appeared in the NSS News. It did soon enough, but in the meantime, you can make a rope ladder by putting figure-8 knots at the correct interval around a regular rope and drop it down, and you just put your foot into each of those successive loops and work your way up. We discovered you had to bend down and put the loop around your boot by hand. And fortunately, that shaft is narrow enough that you could sort of brace yourself against the wall while doing that. I survived that. And eventually, we got pretty competent and at least daring enough to go down to West Virginia on a Thanksgiving weekend from Boston to take a look at Schoolhouse Cave. Other adventures in that time were to meet some rather luminaries, as I said, in their own right, and there's the author of Underground Empire and New England Buried Treasure, Clay. What's his?
Perry.
Why did I forget that? Clay Perry. I think it's the Clay Perry. In fact, we picked him up in Pittsfield and took him out to an NRO meeting. And we often went out to New York City to explore caves in the Schoharie area and thereabouts, one of which was Mitchell's Cave. And Clay Perry, in his book, said it was 300 to 500 feet deep, and I had some doubts about that. And so the grotto surveyed it and found it was about 160 feet deep. And we prepared the first cave map I ever drew, and about the last cave map I ever drew. I never became a cave mapper. Other caves visited the area started my thinking about the phenomena we observe in caves. And the phenomenon here are scallops and flutes on the cave walls. Art Palmer had this same picture with a caver in it in his presentation, and he said in that he told the story about putting a plaster cast on the wall to try to get a mold of the scallops and then not being able to get it off. And I will, however, explain that the person who actually put the plaster cast on the wall while I was in California, and at my request, it was Russ Gurney who did that. I've often wondered if it's still there, but from there, having to compress time and space as I must do here, I moved to California and looked for cavers out there, and one of the ones I quickly found was Howard Shugart, who was at the faculty at the University of California. And in fact, he is the person that he served on the NSS. He's a director at NSS for 1 year and got very familiar with the society. And he asked me if I would care to take on the chairmanship of the NSS Safety Committee. And not knowing what was involved in that, I agreed to do it. Also, among people met in the early days there is Bill Halliday. I have a certain knack for taking pictures of people so you can't see their faces. And I think it's because I'm basically more interested in the environment and the things that are around there. Another caver who joined us in the San Francisco Bay chapter when it was founded is Donald Davis, who many of you may know, and this is in about 1959. And see, that would make it 30 years later, he got the Lou Bicking Award, and a few years after that, he became an honorary member of the NSS. And as I say, I was always attracted to these people who are really dynamic and hard-charging cavers and speleologists, though I myself was never particularly hard-charging in regard to cave exploration. Another person, also in that particular cave, which is Little Burn Cave, is a phenomenon that is ripe for analysis by an engineer or scientist, and that's a cave pearl, and you can see the seat off which it was moved next to it, so it had to rotate there. But if you think about it, as these things grow, they are sure to get slightly out of round, and if they get out of round, they're going to stay out of round and rotate around their probably the smaller radius. And so how it remains almost a perfect sphere is still a puzzle, which I never did address. This is is Al Amon, who is the co-author of the Cave Conservation Policy of the NSS. I caught him facing me because he had no choice. And on another trip, we went with George Moore to Titus Canyon Cave and to do some mineralogy. And George Moore was measuring the pH of samples of minerals to identify them. I don't know how well that actually works, but the cave is really best known for its aragonite. And that introduced me to the puzzle of aragonite. It's a thermodynamic problem. That word thermodynamics is what occurs in engineering. And aragonite is more soluble than calcite, so at first glance it shouldn't form, and therefore the question arises why it does form. The end result of considering that was a paper I wrote on the calcite aragonite problem many, many years ago, with some deductions about that issue. Being in California, I also started to spend a lot of time in the High Sierra, and in this particular instance, it's at the White Chief Cave area in the southern Sierra Nevada, and that's Daryl Tomer, a very well-known caver from that area. And while looking at other caves, and while also in the mountains there, we see other examples of scallops. And so my curiosity about scallops was stimulated by this, but it turns out that these kind of scallops on glaciers do not form by the same mechanism. I'll just let that go at that, and so I never got far into analysis of these. However, the ones on cave walls, like these, again, made me think there has to be a easy explanation. There's literature on this, but the literature at that time said some of it said that these patterns propagate upstream, and some of them said the patterns propagate downstream, and they had other explanations. This became a subject of considerable interest, and I have some close-up photographs of these. And these are scallops at about 6.5 centimeters interval, and the velocity was about a half meter per second when they're submerged, thinking that the water flow that we found there was at least close to the water flow that would occur when they were created. We also went off to the NSS convention, and here is a summary of all the NSS conventions I've been to. So I won't use up slides going to a lot of different conventions. Here's my summary. Whoops. Let's see. Oh, yes, my first NSS convention. What I was surprised by what I've been surprised by is a shift from the formal clothing worn at the early NSS conventions to what we do now. The man on the left is Don Cournoyer, who was at that time the administrative VP and became the treasurer of the NSS not long afterwards. And on the right is George Moore, who at that time was the science vice president, who I had also shown in a previous picture. And now let's get off to the 1960 NSS convention, and here's my summary slide. You can find me there somewhere. Among the projects in the San Francisco Bay chapter was concerned with Black Chasm Cave. We were concerned with the qualified amateur, the dangers of exploring this cave, which is very deep, and linked up with the Nature Conservancy and formed the first joint NSS Nature Conservancy Cave Preserve project. We put a gate on it very quickly. It was a manhole frame and cover. And unfortunately, some years later, a caver spoke inappropriately at a meeting at which the owners of the property, which was a limestone company, were there, and they cut off our access to it because they didn't like what he had to say. After that, however, this is in the Black Chasm Cave, and one of the reasons that it was desirable to protect it. Helictites galore. One of the participants in the early San Francisco Bay chapter was Dave McClurg, and he was on the first scuba diving expedition attempted in Black Chasm Cave. That's when I, as described in the introduction, I learned some scuba diving for that purpose. Another topic that occurred during this period of thinking about caves and going to caves, and in reading all of William Davies' caverns of caves of West Virginia, was the fact that some caves have different numbers of entrances. Lots of caves have one entrance, and other caves have 2 or 3, and fewer caves have larger number of entrances. And so the question arose, well, why can't we extrapolate this to 0 and find out how many caves have no entrances? Now, you can do this on a piece of graph paper and draw a line and say, ho, this predicts that there are a certain number of caves, but it doesn't explain anything. It doesn't explain why there should be those caves that have no entrances. And that's where I started thinking about the process by which there's that arrow I wanted. This depicts that at an initial time, you have here's a lot of caves with n-1 entrances. Pick an n for your own purposes. Here's one with n entrances, or let's say it's 1 entrance, two entrances, and 3 entrances. And over a short period of time, they are going to change the number of entrances by mass wasting and collapse and so forth. And so some of these will lose an entrance and go from, say, 3 entrances to 2 entrances. And some of these will go from 1 entrance up to 2 entrances in that period of time, depending on the rate of that process of mass wasting that's closing and opening entrances. The result is that at that later time, t plus delta t as we say in engineering, there will be a sum of all those that did not change the number of entrances, because some of those also went off these different ways. And you have a pile up on, at that later time here. There's a probability of this happening per unit time, and a probability of this happening. And I figured that, well, a cave ought to gain an entrance more, just in a certain probability of gaining an entrance in a certain length of time, but a cave will lose an entrance depending on how many entrances it has. If it has twice as many entrances, it's more likely to have it is twice as likely to lose an entrance in a given length of time. This leads to what is called a random walk. Caves are walking in this grid among different number of entrances, and there's a mathematical way of approaching that. Okay. Here are some data from West Virginia, actually from Davies's book. It's pretty old data, of course. For all caves longer than 100 feet, of which there are 186 of them. And here are how many caves have each of 0, 1, 2, 3, 4, 5 entrances. These numbers here. Most have 1, a few have 2. It really drops off very quickly. 4 had no entrances. And these are ones found in road cuts, quarries, and of course cavers digging them open. When you apply the model to these, it fits pretty closely. You can compare the number at certain number of entrances right across here. The model fits the number of entrances at 1 and 2 and 3 entrance caves, but when you extrapolate to 0, we discover there are 3,500 caves with no entrances in West Virginia. That's about 20 times the number of known caves, and in fact, it's probably true. Part of the theory also accounts for the fact that the probability of gaining an entrance is proportional to the length of a cave. The longer it is, it's more likely it is to gain an entrance into this process of mass wasting. And therefore, the longer caves, the caves with more entrances are longer, and this is also fit by the mathematical model with the predicted lengths, and you can compare those across here also and see that those predicted average lengths of all the caves with various number of entrances. And the average length of 0 entrance caves is 318 feet, as opposed to 1 entrance cave with 1,050 feet. They don't have entrances because they're small and mass wasting closes an entrance, and they don't have much opportunity and chance to gain another entrance. How do I hit this?
Just push a button.
Yeah, I can't see that. That's the problem.
This is type of plot will appear again later, so I'll explain it briefly. This is the fraction of the caves in the area, so 100% are longer than 100 feet. And it's the fraction of caves that are longer than 1,000 feet, which is something like, this number is 0.2, 0.3, 0.4, 0.5, and so forth, a logarithmic scale. And there's about 20% of the caves that are longer than 1,000 feet, and so forth. When you put all those 0 entrance caves into it, however, it straightens that line out a great deal. And the predicted number of all caves longer than 100 feet, whether or not they have entrances, is this line here. And the fact that this is almost a straight line actually has quite a bit of significance that will come up later. There we go. Well, I finally had to move. I took up a position at University College London in England, and therefore went to the continent, and I ended up staying there for 3 years, and so this is a picture that represents England. Not modern England, but England. I think you all know that Stonehenge. And at this point, I think I also have to admit that I have other activities besides chemical engineering and caving. And one of these I started in San Francisco when I learned Scottish country dancing and Highland dancing.
And so when I went to England, obviously I would look up a club there and join the the Country Dancing Club at University College London, and they had college day. And the people, my compatriots in the dancing club knew I could do the Highland Fling, and so they invited me to give an exhibition for University College London, a college day, and there I am in the middle of the Highland Fling. You can call this an American in London. But I also didn't stay away from caves very long. This is the underground laboratory at Moulisse in France. And went down there a couple of times. They have a laboratory in the cave, and I set up a experiment, in fact involving the calcite aragonite question, in their cave, but I will admit it was a failure because I never got back down to there again to monitor the project, and no one told me that it was doing anything. However, in other locations in Europe, this is the chalet entrance at the Eisriesenfeld in Austria, and in that I visited that in connection with trips to it as part of the Third International Congress of Speleology, which was actually my first stop in Europe. And then later on I went back down again to look at these. And these are scallops. They're in ice, and they are about 140 centimeters, 1.4 meters between the crests. And the flow is about 21 centimeters per second, at least measured at that time with the wind blowing by these. These form by exactly the same process that they form in caves with water and limestone. The limestone dissolves with water flowing past it, and here the ice evaporates with air flowing past it. And this was the key answer to a fundamental question in scallop formation, because when you look at it from an engineering standpoint and the dimensional analysis of the process, the length of scallops, the size, depends on the velocity of the fluid, its density, and its viscosity. And there's reason to think that it only depends upon those things. There's a procedure called dimensional analysis that will combine these into a single dimensionless number. Actually, it is the number of variables, which is 1, 2, 3, 4, minus the number of dimensions involved. And in physical processes, the dimensions are mass, length, and time. There are 3 dimensions in physical processes. So 4 minus 3 is 1, and there's only one dimensionless number you can make. And therefore, since there's only one number, it has to be a constant. That's not an obvious conclusion, but it's this type of number, length times velocity times density over viscosity, is called a Reynolds number. I didn't put the numbers on this slide. When you calculate the Reynolds number for the rock-water interface from Boyden's Cave in California that I showed you earlier, the number comes out to be 23,500. When I calculated it for the air flowing past the ice and these huge scallops in Eisriesenfeld, it comes out to be 21,600. In other words, about 22,000 for both. It's a constant for both of these processes at these tremendously different scales. And that allows you to predict, gives a means of predicting velocity by measuring the length of the scallops. The length is inversely proportional to the velocity, if you rearrange this, and whatever number you can find for this. Oh, good. I can find that button. At University of Michigan, I've got a graduate student interested in this, so we built a water tunnel and used plaster of Paris as a soluble material and generated artificial scallops and flutes. Here are the artificial scallops. This is at a low velocity. This is at a high velocity. actually we got this large difference of size by not just changing the velocity, but by increasing the temperature, because temperature changes the viscosity, and therefore if you reduce the viscosity by heating it up, you do the same effect as increasing the velocity. And both of these have a Reynolds number of 21,000 as laboratory. The cross-section of a scallop, it looks like this, fit an equation to it, and this has become the basis for some attempts to do numerical flow analyses over rough surfaces like this. No one has yet reproduced the actual shape in the mathematical computations of this, so that remains a challenge, and anyone that wants to tackle it is welcome to try. In Michigan, there aren't many caves. There are sinkholes, and here is a typical, probably a worldwide typical sinkhole with cars down in it and all sorts of other debris. The sinkholes in this area actually formed by the dissolution of evaporites at nearly 1,000-foot depth, and the rock collapses up to the surface. And the rock here is limestone, so it forms a more stable cap that can collapse locally to form these very deep sinkholes. Other sinkholes in Michigan, here is a entrance to here's the beginning of a sinkhole, which has not yet opened up to its full width. Below ground, it is nearly 50, 60 feet in diameter, and the throat of it is about 10 feet in diameter. A stream comes in here and flows underground and falls 85 feet inside the sinkhole. That is the highest waterfall in all of Michigan. If in the spring, the water flow is too large, but it fills up to the top. We have a movie that's being prepared for the NSS audiovisual library of an exploration of this, but it's not yet available. All during this period, I was quite involved with the NSS, and I was on the board of the directors for a period, a total of 25 years, if you can believe something like that, of which 4 years I was president. And what I've decided to do is to illustrate this whole experience with one slide. Now, as president, I was at the front of the rope. But the fact of the matter is, everyone pulling on the rope contributes their pull equally. The person back here can pull harder than I am here. And in fact, that's how the NSS functions. It depends on a lot of people pulling together, all contributing their own abilities and strengths to the function of the society. We also went on cleaning trips to caves in Kentucky, removing graffiti from the cave, and eventually found an actual cave in Michigan. And one of the things we did in it was nitrace it, that's fluorescein being put in. It doesn't turn green because the way it's lit, and of course fluorescein itself is orange color. It turns out that this particular cave, between the sump in it and the resurgence is 1 mile, which has never been entered. And in fact, some caves are quite challenging and a lot of fun. And there, after a survey trip in a cave called Kochab Cave, and I was on compass, which was a bit of a problem because when I went up to adjust my light, carbide light, mud fell off my hand onto the compass, and well, things went down from there. This cave became a rather high tourist pressure on it, and we found that people were camping around the entrance, and there were graffiti appearing and so forth. And so the Grotto decided to form a corporation, the Michigan Karst Conservancy, which eventually, in
in 1987 purchased the cave. This is at the same time as the previous slide with the mobs that were invading the cave, so to speak. And we formed a nature preserve there. The nature preserve has trail, this is a sign for it, Highborn Karst Preserve, managed by the Michigan Karst Conservancy. And we put trails through the property. And this illustrates a phenomenon at the Michigan Karst Conservancy that's hard to understand. This gentleman here is Tom Ray, if you recognize him, some years ago. He at one point was president of the NSS. Another president of the NSS, for whom I don't have a picture here, is Dave Luckins. And I was president of the NSS, so we have three past presidents of the NSS going up to this remote area in the North Woods of Michigan, which only had one cave, and having a lot of fun there and doing a lot of good work in connection with maintaining and managing the cave. I've never understood why it concentrates ex-presidents of the NSS. Also at the cave, a session of the National Cave Rescue Commission was conducted in the cave, and a volunteer was hauled out from the end of the cave, which was no easy task. So there are a lot of activities in Michigan like this. As I said, we don't have many caves, so we have sinkholes and other things filled sinkholes. During this time, I was thinking about other things that other interests in speleology. One of which was I read in the books in speleology that the size of a soda straw is determined by the size of a water drop. Now the question is, what determines the size of a water drop? Clearly, it's the size of the soda straw. So, which came first? So I made some soda straws out of glass and made drops and took a look at them. And if you have a very small tube and you form a drop, the drop bulges out away from the tip before it necks in again, just before it falls off. If you have a typical soda straw size, it also bulges out, and it becomes essentially flat here before it starts shrinking again, before it drops off. So you have a big tip here. It never gets out to be vertical edge here, and it pulls in again before it drops off. So I think what happens on soda straws is you have to, if you have a too small one, the crystals can grow out into the drop. And if you have a too big one, the crystals cannot grow out into the drop, and therefore they'll neck down. And therefore, little ones will grow larger, soda straw will grow larger, and the small ones will grow thinner. And just the right size will make that the size at which the soda straw actually formed. This was subject to analysis, and the variables are the tip radius, and we're interested in this angle here, and an angle depends upon the radius, the density of the fluid, the acceleration of gravity, and of course the surface tension. The only dimensions involved are, again, the physical dimensions of length, mass, and time. And given that we have the drop volume is a superfluous one because it depends on what happens with the other ones, the angle will depend upon all the others. So the angle, we have it back down a little bit. The angle, what we're interested in is making this angle, what is this? The maximum value of this angle will depend upon the other variables. Now, an angle is a dimensionless quantity, and all the other variables only form a single dimension. So the maximum angle a drop forms while this angle it takes while it's forming, before it starts shrinking again, is a function only of this set of variables, the radius squared times the density times the acceleration of gravity divided by the surface tension. It's a bond number, and it is called a bond number, and it is another dimensionless ratio. This is dimensional analysis, finding another relationship. The only problem is, what is the relationship between these two? Well, that actually could be calculated exactly. And if anyone wants to do the exact calculation, I invite them to do so. But I did it experimentally. And by measuring the angle and plotting it as the tangent of the angle versus the square root of the bond number, the data points for different size tips from which I was forming drops, the maximum angle occurs here where the tangent is 0, and that is a value of 0.94 for this dimensionless number. So soda straws form when this particular dimensionless number has a numerical value of 0.94. This allows you to predict the size of soda straws forming on the moon, from molten lava, and other interesting places, or with different liquids. Immediately you think about, well, what's going on with stalagmites? Well, stalagmites have a similar, you can take a similar approach, but the stalagmite size is an analysis I have done for minimum diameter stalagmites, but it doesn't yield a dimensionless number that is that applies, so it's somewhat more complicated. But I did take a look at the shape of stalagmite caps. And a rather simple analysis leads to from the standpoint of a mathematician or an engineer, a rather nice differential equation with a rather nice solution. This is the distance from the tip in number of radii of, it's a non-dimensionalized, but the distance from the tip divided by the radius of the stalagmite, and y is the radius of the cross-section of the stalagmite at any distance, also divided by the radius. And in fact, if you look at some stalagmites, they agree with this equation. This is a cross-section of the stalagmite with a broken specimen found in the floor of Ogle Cave and then sliced open to find its dimensions. Okay. Oh, wow. Time is flying. I'm now going to have to zip through it. In Michigan, we did some dye tracing in the sinkhole. Here's the sinkhole, and we poured the dye over where the sink drains. And my most recent project has been consideration of caves as fractal objects. And so here is an object that's called a Menger sponge among fractal people, and it's sort of cave-like. All you got to do is sort of make this in putty and then start stretching it and pulling it around so the passages are longer, and you can only get into certain ones. Some are too small to get into and bigger ones intersect. But it's cave-like. And so the question was, do caves behave this way? And so I set out to do that by filling caves, using cave surveys, using the survey data. I filled caves with what I call linked modular elements and looked at their sizes and to see if they have the same sort of behavior as that Menger sponge does. And in fact, they do. And here is the number of these linked modular elements versus the size of a linked modular element in a plot which is logarithmic, meaning this is 10, 100, and 1,000 rather than arithmetic. And this size is 0.1 meter, 1 meter, and 10 meters. And this is a Little Brush Creek cave in Utah for which the data was provided. And the survey was done, and it forms a straight line of and this is called mathematically a power law, very characteristic of fractals. And Menger sponge, when you do the same sort of thing with it, you get a straight line. And the slope of this line is called the fractal dimension. And for the Menger sponge, it is 2.73, and for Little Brush Creek Cave, it is 2.79. Very, very similar. An interesting number is this one. Now, if the horizontal line in here means that you don't lose any link modular element looking at larger size. Here is a tenth of a meter, 10 centimeter. You don't have any caves that you get those visit at 10 centimeters. And at 20 centimeters, you still don't have many that people map. And you finally pick up some at 30 centimeters or so because they run their survey lines through small holes. And so what is this dimension with its breaks, where you don't have any here and all you need? What is that size? That's the size of a cave explorer. It's essentially the average size of cave explorers. If cave explorers were smaller, this line would continue on up indefinitely. And that's where, in fact, this concept has been used in, as a consideration to cave biologists, because a lot of cave biology is smaller than people. And therefore, the bugs are all up in here, rather than, we see them down in here, but they're really up in there. The lengths distributions, here are the one I showed previously is West Virginia, and it's a nearly straight line. And the same thing done for, if you combine the length information, which is also a straight line in these log-log plots, with the link modular element data, you can predict the total volume of space in an area. And this is in Pennsylvania, using the published information about caves of Pennsylvania. In the range 1 to 100 meters, it predicts 1.3 to 10 to the 7th meter cubed of space. This includes caves that have no entrances. And we can carry this on down here, and I go down to here, which is, what's that, 1/10 of a millimeter. The space down to 0 to 1/10 of a millimeter is 1.1 times 10 to the 6th cubic meters in Pennsylvania, and I dare you to prove I'm wrong. I'm concluding with this slide because of the various things I've looked at have just been at the very beginning of the exploration of these ideas of things like fractals and so forth, and dimensionless numbers applied to caves and so forth. And there's a quotation I'd like to read by another person who did a lot of very interesting work based on very limited information. And he said, quote, "I was like a boy playing on the seashore and diverting myself now and then, finding a smoother pebble or prettier shell than ordinary, whilst the great ocean of truth lay all undiscovered before me." That was Isaac Newton, a much brighter luminary than myself. Thank you very much.
Thank you very much, Rane. Rane has agreed to visit with us out in the lobby. We have to be out of this room in a couple of minutes. So if you'd like to take a picture with Rane or have him sign a publication,